Well, hello everyone. Today I would like to discuss with you how to add fractions. But first let's just do something very familiar. Something as easy as 2 plus 3 equals 5. And then we will slowly build it up to adding fractions. And you will see adding fractions concept-wise is exactly same as adding 2 plus 3 equals 5. So when you first learned how to do 2 plus 3 equals 5, perhaps you proceeded as follows. 2, you put up 2 fingers, and then 3, that's 3 more, and you started counting after 2. After 2 is 3, 4, 5, and that's how you got your answer of 5. That's how you counted 2, 3 with what we call discrete objects. So now here's how you can view 2 plus 3 on the number line. So let's look at the number line. And let's recall that this point is 2, and also we agreed that the length of this segment that starts at 0, ends at 2 is also 2. That's what we agreed. Okay, and also remember on the number line, we have this distance equal to this distance equal to this distance and so on. 2 can be thought of as the length of this segment, length 2. 2 plus 3 means attached to this segment of length 2, another segment of length 3. So that would be this, 1, 2, 3. If you look at this segment, this is of length 3. Now notice how did my attachment. I have my segment of length 2, and exactly where it ends, I start the next segment of length 3. So this way of joining one segment end to end with another segment is called concatenation of sectors. So that's what we just did. We took a segment of length 2 and concatenated with it a segment of length 3. Then what do you get? Then we get a long segment of length, you guessed it, 2 plus 3. And what is that? Well, if you start at 0, and the way we arrange the number line, the answer 5 shows up right at your right hand point. So that's how we can add 2 plus 3 on the number line. We start at 0, your first segment starts at 0 and ends at 2. That's your length 2. And then the next segment is length 3. 2 plus 3 is the length of this long segment, and the answer 5 shows up here. So that's how we do that. Now let's see how we can use the same idea and add fractions. Let's go over to the other board. Let's look at what I have on this board. I have 2 over 7 plus 3 over 7. How do we add fractions? Well, exactly the same way as we added whole numbers on the number line, which is, look at a segment of length 2 over 7. So here's the number line, and here's the unit segment, 0 to 1. The unit segment is cut up into 1, 2, 3, 4, 5, 6, 7 pieces. And when we do so, each of these points is a fraction, and you know how to label those fractions. That's exactly what I've done here. So 2 over 2, this point is 2 over 7. The length of this segment, we said, is also 2 over 7. That's our agreement. So, and also each of these tiny segments, its length is same as this segment, which is 1/7. So this is a copy of 1/7, this is a copy of 1/7, this is a copy of 1/7, and so on. Now let's look at how we may define how to add two fractions. What makes sense? Well, if we follow the procedure we did for whole numbers, 2 over 7 is the length of this segment. And we said we can take a segment of length 2 over 7, a segment that starts at 0 and ends at 2/7, and then right where it ends, attach to it another segment of length 3 over 7. Well, this is 1 over 7, 1 over 7, 2 over 7, 3 over 7. So this would be my second segment of length 3 over 7 added to the first segment. If we do that, what do we get? We get this first segment put together end to end with this segment. So that means we get this long segment. What is its length? Well, it starts at 0 and ends at this point, and that point is 5/7, and that 5/7 is also the length of this segment. So the answer to 2/7 and plus 3/7 is right there, staring at you, 5/7. And let me write that here, 5/7. And look at what happened. It sure looks like the previous problem. It looks like really 2 plus 3 is the 5. And that is exactly correct. Why is that? Look at this. Here's another way of looking at it. What is 2/7? 2/7 is really 2 copies of 1/7. So 1/7 plus 1/7. That's your 2/7. And we add to it 3/7. 3/7 is really 3 copies of 1/7. 1/7 plus 1/7 plus 1/7. So if you do that, how many total copies do you have? Here's your 2 copies, and here's your 3 copies. So that is 5 copies of 1/7. Another name for 5 copies of 1/7 is really 5/7. There it is. So what are we noticing when we have to add fractions with the same denominator? You're perhaps noticing that's really same as not getting another fraction with the same denominator and simply adding the numerators. The reason that's happening is due to this argument here. 2/7 is 2 copies of 1/7, and 3/7 is 3 copies of 1/7. So when we are adding fractions with the same denominator, we're simply counting the total number of copies of the same thing. So 2 copies plus 3 copies, that's 5 copies. Of what? Of just 1/7. So that's how we get it. The concept is exactly the same. On the number line, this piece is of length 2/7. We attach to it another piece of length 3/7. Then we get a long segment, and its length is 5/7, and there it is, 5/7, at that right-hand point, staring at you. So that's how we add fractions with the same denominator. Now let's look at this example that I have on the board. I would like to add 5/117 and 9/117. Now clearly drawing pictures is not a good idea for this, because 5/117 is 5 copies of 1/117. 1/117, well, the denominator tells me if I did draw the number line, I would need to cut up the unit segment into, you're right, 117 equal pieces. And I certainly do not want to do that. So I think about the previous example, and I kind of think logically, how did we get the answer in the previous example without the number line? And let's try to do that. Well, 5/117 is 5 copies of 1/117. 9/117 is 9 copies of 1/117. Adding means we're simply counting how many total copies of the 1/117 pieces. Remember, 1/117 is the length of the tiny piece. When you start out with the unit segment and cut it up into 117 equal segments, equal by length, then the length of any of those tiny pieces is 1/117. So in this addition, all we're doing is we're taking 5 of those tiny pieces, a copy of 1/117, and then adding it to 9 of those tiny pieces. So how many of those tiny 1/117 pieces are we going to have? Same as 5, adding 5 and 9, because we have 5 copies of the tiny piece, 9 copies of the tiny piece. So that's really 14 copies of 1/117. That's really same as writing 14/117, because 14/117 is really 14 copies of 1/117. So now I think you get the idea of how to add fractions with the same denominator. same denominator tells you you have the same type of tiny pieces, and the numerator tells you how many of those tiny pieces you have. And adding just means adding the numerators when the denominator is the same. So I'm sure you can make lots and lots of those examples. You can make them up and write them all down. Mathematicians kind of like to observe patterns like that, exactly what we did here, which is when you add two fractions with the same denominator, you get a fraction with the same denominator, and the numerator is just the adding of the numerators. And we like to say that using some symbols, and I will go over it, symbols meaning letters. Let me go over it and let me explain why we do it, how we do it, and so on. So let's read what I have out here. So let's read it together. Suppose A, B, and C are whole numbers and C is not equal to 0. And the addition algorithm, that means the algorithm that tells us how to add fractions of this type, it goes as follows. A over C is just a fraction, but where A is a whole number and C is any whole number, but it cannot be 0. So C is a non-zero whole number. And add to it another fraction, B over C. Notice both these fractions have the letter C in the denominator. So C is the same non-zero whole number. And what happens when you add them together? We're saying this is how we define addition, because it makes sense based on the examples. We're saying that equals a fraction with C in the denominator and the numerator is A plus B. You can also think of this as A over C is A copies of 1 over C added to B copies of 1 over C. That's same as A plus B copies of 1 over C. That's what the addition algorithm is telling you. Okay? And why do we use letters? We use letters to signify that instead of writing down lots and lots of these problems, well, you can write an infinite number of problems, because you can pick anything in the numerator or anything in the denominator, and then anything in the numerators, and then these numbers, you have to pick another non-zero whole number to write up such a problem. Well, all of those problems, all addition problems, addition of fraction problems you can think of, where the denominator is same, all of those are packed into this equation. Why is that? Look at this. If I choose A as 5, C as 170, B as 9, this is exactly this math problem. Do you see that? So after you do a lot of example, you can pack all the knowledge, all your hard work of a lot of such problems where you're adding two fractions with the same denominator but different numerators. All of the hard work is just packed into this little equation with letters in it. And remember, whenever you use letters, then you have to say what the letters are, which is why I wrote out here. These letters, not your English letters. We wrote them, but those are really whole numbers. Which whole numbers? Well, you decide. If you decide, let's write another problem. Let's decide C is 82. So I would like to add two fractions with the denominator 82. A and B are again whole numbers. We can pick any, and let's pick 10 and 40. What do we get? If you remember this addition algorithm, then that is simply 82 in the denominator. Numerator is just 10 plus 40, which is 50. And that's how you get the answer. Also think about, why do we define adding of fractions in this manner? For that, go back and review the examples that we just did on the number line. What makes sense? How do we add fractions? And in that I said A over C can be thought of as a segment of a certain length A over C. Concatenate with it another segment of length B over C. and we saw for some specific examples that this way of adding makes complete sense. When we put together two short segments, then the addition is really the length of the long segment. That's the simple idea we used to come up with this addition algorithm. So make sure you understand the examples we did, and then make sure you can remember this addition algorithm with letters in it, and also remember what those letters stand for.